properly phrasing or describing the null and alternative hypothesis. I just want to just go over that quickly so that we can put that away for good. And there's a couple of instances where it comes up in the third exam. Okay, so for starters, one of the first things that we dealt with was, well, first of all, we first learned about confidence intervals, and we learned about central limit theorem and so on and so forth. And that really led into the t-test, right? In other words, a test where we can compare the means of two different populations. The mean of population 1, null hypothesis would be it's equal to the mean of population 2. That's our null hypothesis. Our alternative hypothesis was the mean of population 1 does not equal the mean of population number 2. Okay, so that's pretty straightforward. We then would take our samples. If it's a single sample test, then we're only taking a sample of one population, not both populations. The other population we know. So for instance, we might know that this is equal to 120. mu2 is equal to 100. So we literally could just write 120 instead of writing mu2, since mu2 is known to be 120. So that we only had to take a single sample because in order to get an estimate of mu1, because we needed that x bar instead, because we didn't know the population of this other, the mean of this other population. So you might, for a two-sample t-test, you might use mu1 is equal to mu2 as your null hypothesis, and of course, for alternative, mu1 is not equal to mu2. For a single sample t-test, you might say mu1 is equal to some number, whatever that number is. Okay, or you could also use mu2 if you really wanted to, knowing that it's 999. Okay, now there are some occasions where we are comparing the means of 3 or more groups, right? So our null hypothesis there is that all of the means are equal, just like before. mu1, population 1 is equal to the mean for population 2 is equal to the mean for population 3 is equal to the mean for population 4 is equal to the mean for population n, right? And just keep going and so on and so forth. It could be as many groups as many populations as you want, right? And the idea is that we start off with the null hypothesis that all the means are equal. Of course, in order to do this, this has to be a numerical variable, because you don't get means for categorical variables. Like there's no average number of right-handers and left-handers. There's either left-handers or right-handers, a proportion, but there's no average. Okay, so that's the way we would phrase that. Now, in order to avoid having to repeatedly do the t-test for every different comparison for all these different means, we use analysis of variance. And indeed, this is our null hypothesis for analysis of variance. Our alternative hypothesis for analysis of variance is not mu1 does not equal mu2, it does not equal mu3, is not equal to mu4, and so on and so forth. It's not that, because the ANOVA test does not compare all of that. The ANOVA test comes up with a p-value, a value for ANOVA that's greater than the critical value for ANOVA, right? Or a p-value that's less than 0.05. When it comes up with that, that means that at least our alternative hypothesis should be, instead of this, our alternative hypothesis should be at least 2 of the means are different. Okay, when you've completed your analysis of variance and you've exceeded the F critical, or use SPSS, you've gotten a p-value or significance that's less than 0.05, well, then you can say that at least 2 of the means are different. Or another way to phrase that, at least 1 of the means is different from some other mean. Same thing, right? 2 means different. At least 1 of the means is different from 1 of the other means, right? Basically, kind of another way of saying the same thing. But we need to say that because we can't say all of the means are different. And we don't want to write it that way because that would be incorrect. That would make it look like we think we proved that all of the means are different. And in fact, you don't know if they're all different. You don't know which are different until you run the post hoc tests. And when you run in SPSS, you run the post hoc tests. Well, then it compares mu1 against mu2, and mu1 against mu3, and then mu1 against mu4. and then mu2 against mu2, and mu3, and so on and so forth. It does all those permutations and gives you a significance, let's say 0.65, 0.5, 0.001, 0.2. So you can see if the significance is less than 0.05, when these are the two means that are different from one another. And maybe you get another one. Maybe you get one that's 0.04. Maybe there's more than two means that are different, right? But you haven't proved that all of them are different, or at least you haven't proved it until you test it with the post hoc tests, right? Okay, so that's how you would do that. So that's how you would phrase the null hypothesis there. Well, let's move on to the ones we're working with now, because now, for the final part of our semester, we're working with categorical variables and numerical variables compared together. Categorical, and numerical, Okay, so categorical, what could that mean? Okay, categorical, or we could also call it numerical, nominal. Categorical versus categorical variables. Okay, so let's see, what could that mean? Let's say that means gender and diabetes. Maybe we want to show if there's some relationship between gender and diabetes. Okay, well, how would we show that? See, well, gender is a categorical variable. It has two values, male and female. And diabetes has two values. Either you're diabetic or you're not diabetic, right? If we're defining it that way. Right? So in that case, what we do is we set up a contingency table. We take all of our males and all of our females, and we put them in a row. So this is all our males. Let's say we have 100 males. And this is all of our females. Let's say we have 100 females that we dug into this study. And then we test them. How many of the males have diabetes? Let's say it turns out that 20 of the males have diabetes and 80 of them don't have diabetes. Right? Well, how about the females? Let's say 15 of the females have diabetes and 85 don't have diabetes. They won't always be nice even numbers like this, but you know that's what we happen to have in this population. Well, let's see, out of 200 people that we surveyed, 100 males, 100 females in this population that we randomly selected in this population, turns out 35 of them have diabetes and 165 of them don't have diabetes. So 35 out of 200 have diabetes. So the prevalence in this population overall, males and females, the prevalence overall is equal to 35 over 200. Or in other words, that's going to be 17.5%, or 0.017, excuse me, 0.175. I think I'm right there. Yeah, I am right there. Okay, that's our prevalence in this population. Okay, so now we say to ourselves, you know, if there had been no difference between males and females, I would expect them to both get diabetes at this same rate. So in other words, we would have expected that for 100 males and 100 females, females, that we would expect out of 100 to get 17.5 males that have diabetes and 17.5 females that have diabetes, and 82.5 that don't in each case, right? This adds up to 35 and 165, just like before. Right? So this is what we would have expected. And we know when we do our chi-square evaluation, what we're doing is we're looking to see how big is the difference between what we expected to get and what we actually got. Right? And we would do that by taking the observed values minus the expected values, square them, divide by the expected values, and then we would do that for each one of these 4 squares. Right? So we'd wind up with 4 numbers from this, and we'd wind up with a total for our chi-square value. So let's say chi-square happens to equal 4.2 in this case. Well, then we could go to our chi-square table and look up what the critical value is for chi-square for 1 degree of freedom. Why 1 degree of freedom? Because in this case, our tables, 2 by 2 table, we have 2 rows, 2 columns. So rows minus 1 times columns minus 1 tell you how many degrees of freedom you have. So 2 minus 1 is 1 times 2 minus 1 is 1. 1 times 1 is 1 degree of freedom. As it happens, that's equal to 3.84. You can look it up in the table. So we want to see if our calculated chi-square value exceeds. Now I made these numbers up. It doesn't really look like you would that it would get that high if I had to guess right now. But I made these numbers up. So let's say it came out to 4.2. Did our calculated chi-square exceed the critical value? And it did. So we can reject our null hypothesis. Notice I didn't talk about what the null hypothesis is yet, right? Well, in SPSS, we could actually do this, have SPSS actually make this calculation for us so that we don't have to worry about figuring out what the expected values are and doing all these calculations. We can just have SPSS calculate it. It would calculate the same chi-square value, right, for us that as we did here, as we got here. But it would also tell us what the p-value is, what the probability that we would get that big a value if these two, if the null hypothesis was true. Still waiting on the null hypothesis. So if this is less than 0.05, right, then we can reject the null hypothesis that there was no difference between males and females as far as diabetes rates, right? So in this case, since we already know that we wind up rejecting the null hypothesis, it's a sure bet that the p-value is going to be less than 0.05 when we actually do the calculations. Don't do these numbers because I don't know if they really come out to 4.2 or not. Well, there's another calculation that we can do also, and we can do relative risk or relative rate, and we can do odds ratio. And what is that? Well, that's another way of looking at the same data. So the odds ratio is going to be 20 for males. The rate at which males get diabetes is 20 out of 100. So that's equal to 0.2. That's the rate. What's the rate for females? 15 out of 100. So that's equal to 0.15. Right? So what's the rate ratio, also called the risk ratio? That the ratio means you put one over the other, so 0.2 over 0.15, and that's going to be equal to 1.33. Right? So males get diabetes at 33% more, 1.3 times as often as females do. What's this odds ratio? How does that work? Well, it's the same deal, except we calculate the odds differently. The odds are, out of 100 people, how many of them have diabetes over how many don't have diabetes. So the odds ratio is going to be 20 over 80 for males, which is going to be 0.25. And for females, it's going to be 15 over 85. And that's going to be equal to, I don't know what it's going to be equal to, so I'm just going to estimate. I'm going to say it's 0.15, just a wild guess. Right? I'm going to put this over this, and it's 0.25 over it. So the odds ratio is the odds for males divided by the odds for females, and it's going to be equal to 1.67, let's say, for argument's sake. So that's our odds ratio, that's our relative risk. Both of them indicate there's greater risk for males, and the odds are greater for males that they're going to get diabetes. Right? So that's how we're looking at that. But the only problem here is that gives us an idea of what the comparison is for males and females, the proportions are for males and females, but it doesn't tell us if it's statistically significant. So what we have to understand is that in order for us to say that this is that males and females get it at a different rate, or the odds are different, we have to look at, well, what is it if males and females weren't different? What would it look like? Well, what it would look like is we might see 20 males out of 100 and 20 females out of 100, both getting it at the same rate. So that would be 0.2 over 0.2 is equal to 1. So if the risk ratio or the odds ratio is equal to 1, then males and females get the diabetes at the same rate. Well, let's see what we have. We have this, and we also have this idea of chi-square. So what are our null hypotheses going to be? Well, number one, we can't say that the mean for males is equal to the means for females because there are no means, right? There's no mean. This is categorical data. There's no average. It's not like weight or BMI or something like that. We can't calculate an average for males or females. Like we would have some, the average person would be half male and half female. It doesn't make sense, right? So we can't do that. So instead, we have to describe this in a different way. And one way is doing that is for chi-square is to say that there is no association between gender and diabetes. That would be our null hypothesis. And what would be our alternative hypothesis? There is an association between gender and diabetes. So that I can't tell you how many people got this right at this point. And then on the homework, they did their calculations and they said, okay, I can reject the null hypothesis. There's no association between gender and diabetes. Even when they wrote here the alternative hypothesis, there is no association. So the right answer would be if you can reject the null hypothesis, that there is an association, that being male or female does change whether or not you're likely to get diabetes. There is an association there, right? So that's the way we would express our null hypothesis for chi-square. Well, how about if you're using, since this is a 2x2 table, see if it were a 2x3 table, 60 and 60, maybe it could be have diabetes, don't have diabetes, maybe pre-diabetes, could be another table. See if it's 2x6. We can't do odds ratio because it's just like one over another. We can't do it with 3 boxes here going across. We can calculate a chi-square. We could do chi-square for a 2x3 table, by just different number of degrees of freedom. We do look at a chart for a different critical value of chi-square, or we can just use SPSS. It'd work out fine for chi-square, but we can't do odds ratio or relative risk unless it's a 2x2 table, which in this case it is. So what would our null hypothesis be for relative rate or relative risk? It would be, our null hypothesis would be the relative risk is equal to 1, and our alternative would be the relative risk is not equal to 1. And how do we know that we can reject the null hypothesis if we don't have a p-value? Well, what we do is we calculate, or we have SPSS calculate, a confidence interval, a 95% confidence interval for the true relative rate. And if the confidence interval doesn't contain 1, in other words, if it's 1.33, we determine that the relative rate is 1.33, and our 95% confidence interval for the relative rate for the entire population turns out to be 1.1 to 2.0, right? What does that mean? That means that we're 95% sure it's not 1. We're 95% sure that the true relative rate is between 1.1 and 2.0, means we're also 95% sure it's not 1, because 1's not in between there. So if 1 is not in between, within our confidence interval, we can reject the null hypothesis and say the relative risk is not equal to 1. Same thing with odds ratio. We can do the same thing with odds ratio. Null hypothesis, the odds ratio is equal to 1, and our alternative hypothesis would be the odds ratio is not equal to 1. So all 3 of these are perfectly legitimate ways of doing describing a null hypothesis test, a hypothesis test for a categorical variable that in this case happens to be a 2x2 table. And so now what about if we have, what else did we look at? We also looked at numerical variables. And what we were looking at is looking at the idea that how can I tell if I have 2 numerical variables? Let's think of 2 numerical variables. Let's say height and weight, right? We want to see if there's an association between height and weight. So we randomly sample 25 people. And each one of those 25 people, we're going to measure their height and weight. So I'm going to use inches, let's say 69 inches and 135 pounds, and 72 inches and 205 pounds, and 16 inches and 110 pounds, and so on and so forth. So now, if I do that for 25 people, I want to know, is there an association between a person's height and a person's weight? Well, and of course, we know that that's going to be true, right? So how would we approach this? What would our null hypothesis be here? Well, before I can tell you what our null hypothesis is here, I'm going to talk about what we're going to do with this first. So what we're going to do with this is we're going to take a look at this, and we're going to plot these values on a scatter plot, an XY plot, right? So this is 0, and this is 100 inches, and this is 0 and 300 pounds, we're going to take each one of these 69 and say 200 pounds, 69 and 135. Let's see. I'm going to plot. I'm going to make the x-axis height. So that's going to be 100 inches, and weight going to be over here, 300 pounds. So 69 inches will be over here somewhere, and 135 pounds going to be over here somewhere. And then I'm going to plot each one of these. Right, so there's a dot there, there's a dot there, there's a dot there. And I can see that there is a linear relationship here. As the height goes up, person's weight tends to go up also. Not everybody. In other words, this person over here is taller than this person, right? They're further along on the height axis. This is height, this is weight. They're further along out on the x-axis. They're lighter than this other person who's a lower value for height, right? So they're before this value for height, but they weigh more, right? So it's not a perfect relationship, but it's a fairly good one. And we can actually define a line which goes through there, which is a kind of a best fit line. And we can calculate how far off all of these different values are. I won't go into, again, the idea of the squares of the differences here, these residuals, the squares of all these differences or residuals. Balance it, in other words, getting them so that they're the smallest number possible when we add them all together. But based on how close these are to a straight line, we can calculate, or SPSS can calculate a value for rho, which is Pearson's correlation coefficient, right? So rho is for the population. We call it R when we're talking about it's a sample. So in this case, R is equal to, and I'm going to take a wild guess. First of all, I know it's a positive number, right? That's for starters. And second of all, I know that it's going to be a pretty good correlation. And I know that if it's the perfect correlation, with both of them going up, in other words, as one goes up, the other goes up, that's going to be equal to +1 for perfect correlation. For a perfect negative correlation, it's going to be equal to -1. That means everything's going to fall directly on a straight line, sloping downwards. Okay, so in between those, so we can have any value in between those things, including 0. And when it's 0, it means that there's no association at all. In other words, this looks basically like a cloud. I can't make dots here. If I punch too fast, it thinks I want to draw a straight line. Right? So it's going to look like kind of like a cloud. There's not going to be any relationship at all. Right? So let's take advantage of that. And we can phrase a null hypothesis verbally, saying that there is no association or no relationship between height and weight. Or an alternative hypothesis is there is an association between height and weight, right? So in order to reject our null hypothesis, we have to show a null hypothesis. Another way of saying there's no association is R is equal to 0, rho is equal to 0. Another way of saying that there is an association is that rho is not equal to 0, right? Could be at some other number, but just not 0. How do we test that? Well, we use SPSS to calculate what R is, and we look for the significance, the p-value or significance. And if it's less than 0.05, we know that the difference between the R we calculated and 0 is statistically significant, and we can reject the null hypothesis. Okay, so that's the way we would phrase a null hypothesis in a correlation. Well, we went a bit further. We decided that, hey, since this is a straight line that we've drawn, we can say that that straight line represents this association. It's a formula. Y is equal to the y-intercept, some constant called the y-intercept, plus some value b, the slope b, times the value of x. And what is that? That's the weight is equal to the y-intercept plus some slope, the slope of the line times the person's height. Right? Well, how do we calculate all that? Well, we take that line and we calculate how SPSS or other software will calculate that line for us, and will give us a value for that y-intercept, which we'll call constant. and it will give us a value for the slope, which it will say it's probably will describe it as the value for the relationship between the height and the weight. It'll give us a different value for that. So if the y-intercept is 20 and the slope is 2, well, then we could say that the weight is equal to 20 plus the slope, which is 2, times the person's height. Now, I'm just making that up, so it's not really that number. I'm going to do an example of this in a moment. So when we do this for correlation, we're looking for this relationship. One other thing, the R value, we want that R value to be as close to 1 or -1 as possible, because that would be a perfect correlation. But we're not going to get perfect correlation unless the two things are related, strictly related anyway, like in physics. So we're not going to get that ever, right? Most likely. So when we do this, we know that if we have an R value of 0.9, we have a really good correlation. If we have an R value of 0.4, we don't have quite as good a correlation, not quite as good an association. Now our line that we're producing is not going to be as predictive, right? So how would I handle it? Well, what does that tell me? Well, we can take the value R and we can square it. If we square this R, 0.9, R squared is equal to 0.81. In this case, R is equal to 0.4. There's a correlation. It's not as strong, right? 0.4 times 0.4 is 0.16, right? Much smaller number. R squared is a much smaller number. R squared is called the coefficient of determination. And what that means is that we can use R squared to predict that 81% of the variability in the y-axis or the dependent variable is predicted by the value of the x-axis. In other words, 81% of the value of a person's weight is predicted by their height. Other things influence it also, but that's in this case. Well, if R squared, if R was only 0.4 and it turned out to be 0.16, then the influence that height has on weight is much smaller. Only 16% of the variability in weight is predicted by knowing what a person's height is. So that means there must be other variables that we haven't tested that have a bigger influence on what a person's weight would be than their specific height. Right, so that's how we would use that R square value. So let's do a couple of quick examples. For the R square, should we use adjusted? I would say for our purpose, R square takes into consideration a couple of things, including sample size and something called collinearity. But I would first say for our purposes, in simple linear correlation, if we have a decent size sample, like not 10, right? And for the test, I don't remember what the sample size of the test. Now I'm thinking about that. Trying to think what I should say. But for our purposes for the test, I would use the simple linear R squared or simple linear correlation for R. So now what I wouldn't use the adjusted value for R squared. Okay, so now in fact, now that you brought that up, when I go back and take a look at it at the exam, I'm going to make sure that Blackboard accepts the R square value, the unadjusted R square value, but that the range of answers that it will accept and say correct include the adjusted value. So even if you use that one, it should be marked correct. I'll go back and change that. I'm glad you brought that up. Okay, so let's give this a quick try. Okay, so I have a couple of databases here. So let's try this one, paper and air. Okay, so this is, I think I ran across a study somewhere that compared whether or not there were more germs in the air from using one of those using paper in a washroom versus using one of those air, supersonic air blowers. So I'm going to take a look at that right now. And first thing I'm going to look at is what kind of variables that we have here. Okay, here we go. Good. Okay, I don't see any data yet. nothing there. I don't need the output window anymore. And I don't know why I don't have any data, so I'll open it from here. Open data, desktop, paper versus air. Okay, work that time. Okay, so what do I have here? I have a one variable called hand dryer, another variable called illness. And they are nominal variables. Their categories are nominal variables. And the values are, for the first one, it's paper and hot air, type of mechanism they have in there, or the type of mechanism that a person might use. And the output, the other variable, illness, is 1, got ill, or 2, didn't get ill. In other words, did they get the flu that year or something like that? Okay, so we're going to go over here to our data view. See how much data we have. We have a bit, it's a pretty good size data set, right? Okay, so we have a lot. So, for instance, person number 7, he used paper and he got the flu. Person number 29 used paper, he didn't get the flu. This person used hot air and he didn't get the flu. This person used, and so on and so forth, whatever it turns out to be. So, what kind of statistical test can I do here? I have a 2x2. I have a something that can wind up being a 2x2 table. In other words, hand or air is in the rows, and whether a person got sick or didn't get sick is in the columns. So I can make a contingency table. So what kind of statistical tests can I use here? Well, first of all, because I know I can create a contingency table, analyze descriptive statistics, cross tabs, and let's put the type of hand dryer in the rows, and whether a person got a respiratory illness that year in here, and let's see what it looks like when we have it in a 2x2 table. Good work. Chi-square and odds ratio. That's and relative risk also, right? So there's 3 ways I could analyze this data. I could do a chi-square test, right? Because it's 2x2, and because it's a 2x2 table, I can also do the odds ratio, and I can also do the relative risk or the relative rate. I could do all 3 of these tests. So what would the null hypothesis be? Null hypothesis would be that there's no association between what kind of hand drying apparatus you use and whether or not you got ill. Okay. Well, how about if I want to do odds ratio? Well, odds ratio would be 19 out of 27 got ill. That among the people that use paper, out of 46, 19 got ill, 27 didn't. So the odds are 19 over 27. For hot air, 10 over 42. So I can take 19 over 27 divided by 10 over 42, and those are my odds, but I need to know my confidence interval to see if it's within the 1. And for my relative risk or relative rate, 19 out of 46 over 10 over 52. And I also have to test to see if that is different than 1. So in my null hypothesis, for chi-square, it's null hypothesis is there no association between which type of device you use and whether you got sick. My alternative hypothesis is that there is an association. In other words, it made a difference whether or not you used paper or hot air because it wasn't equal. You didn't get ill at the same rate for paper and hot air. There's a difference between them. So that's my alternative hypothesis. Well, if I'm going to do relative risk, I can just simply use 46. I can use relative risk is equal to 0 as my null hypothesis. Relative risk is equal to relative risk is equal to 1 for my null hypothesis, and relative risk is not equal to 1 for my alternative hypothesis. For odds, the same thing. Odds ratio is equal to 1, my null hypothesis. Odds ratio not equal to 1 for my alternative hypothesis. Let's test all of these. So I'm going to go up here to analyze. I am going to go to descriptive statistics and crosstabs, and I'm going to ask SPSS to calculate for me the chi-square value and the risk values. I'm going to click continue, and I'm going to click OK. Okay, so now what did I get here? What are my results here? Well, my chi-square value is 5.7. Okay, so 5.7. Okay, 1 degree of freedom. So now I'm going to stick with that. I'm not going to worry about continuity correction. 5.7. I think I mentioned to you for 1 degree of freedom, what was the critical value of a chi-square? It was 3.84. So we've exceeded it. So right there, I already know in my head I can reject my null hypothesis. But I can also see that SPSS has actually calculated for me the probability that we would get that big a chi-square if the null hypothesis were true. In other words, there's only a 1.7% chance that we'd be wrong if we reject the null hypothesis here, right? So I can reject the null hypothesis, it's less than 0.05, and I can accept the alternative hypothesis that there is an association between paper and whether you use paper or hot air and whether or not you get ill. Okay, well, what about the odds ratio? Let's go down here. The odds ratio is equal to 2.9. So in other words, based on what we have in our table, the odds of getting sick is 2.9 times as great if you use paper versus if you use hot air. Okay, well, that's all and good, but what's the 95% confidence interval? Maybe that 2.9 is just due to chance because it's too small a sample. But it turns out that the 95% confidence interval, we think it's 2.9, but we're 95% certain that the true population rate of paper versus air and getting ill enough, true population rate is 1.2 to 7.3. So we're 95% confident that it's not 1 because 1 is not between these two. 1's outside of this range, right? So 1.2 to 7.3, since 1 is not between them, we can reject the null hypothesis and say that the odds ratio is not equal to 1, right? And how about this is the 2.14 is the relative risk, right? And again, with the relative risk, the 95% confidence interval is 1.1 to 4.1, so excludes 1, so we're 95% certain we can reject the null hypothesis. In other words, we can reject that relative risk is equal to 1 and say relative risk is not equal to 1. Right? So that's the way we would use this information. Okay, so now what about our correlation and our regression? Okay, let me pause for a second there. How you guys feel about that? Are you okay with this? Okay, good. So let's open up another data set. And I'm going to open up the birth data set because I'm not sure that I have another numerical data set with numerical data. So I'm going to say open data. Let's open this up. Let me find some numerical data here. So what numerical data do we have? We have the mother's age, the weight gain during pregnancy. That's a numerical variable. We have the weight of the baby, and we have, well, how about that? Let's take a look to see if there's a relationship between the amount of weight the mother gained and the birth weight of the baby. You would think, wouldn't you, that there would be a relationship between those two. But until we test it, we don't know for sure. We're statisticians. We have to figure this out, right? We have to prove this. We can't just take it for granted. Okay, so I am looking for an association between the amount of weight the mother gained and the weight of the infant. I want to see how strong an association that is too. Okay, so first thing I want to look at, they're both numerical variables. First thing I want to look see is there correlation? Is there some association I can see graphically here? So I'm going to go up to graphs, to legacy dialog, to scatter dot, and I'm going to tell it I want a simple scatter dot where I'm going to put the mother's weight in the x-axis, and I'm going to assume that's going to predict the baby's weight. The mother's weight gained during pregnancy, and put that into the x, and then put the weight of the child in ounces into the y-axis. Okay, so I'm going to click OK, and let's see what our graph looks like. Okay, wow, let's see. It's kind of hard to see, isn't it, right? So, but it does look like that there is some positive association there, right? Because I see some low values here, but I don't see low values up here. I see mostly higher values up there. So I'm going to continue with this analysis. I'm not in love with this graph, but I'm going to continue with this analysis anyway. Would have thought it would have been better in this, right? Okay, so let's take a look at this. Let's take a closer look at this. I'm going to calculate our correlation, analyze our R value. Let's analyze, say, correlation bivariate. And I'm going to move, and what is our null hypothesis now? Well, if there's no association between the weight gained and the birth weight of the baby, R, the correlation coefficient, is going to be equal to 0. If there is an association between the two of them, then the R value is not going to be equal to 0. In other words, our alternative hypothesis is R is not equal to 0. And we're only going to reject our null hypothesis if we have enough evidence to do it. In other words, if the probability of getting that high an R value is less than 0.05, in other words, if our significance of p-value for R is less than 0.05. So let's give it a try. So complete, let's see, marital status, weight gain during pregnancy, and the weight of the child in ounces. Put that in there, and I'm actually going to calculate my Pearson's chi-square on my Pearson's R. Okay, and see what I get. Well, my correlation is, boy, it's amazing. What a weak correlation, right? 0.222, right? So 0.222 is a positive correlation. As the mother gains more weight, the weight of the baby tends to get greater as well. And is that can I reject the null hypothesis? Let me ask you, can I reject the null hypothesis that my null hypothesis R is equal to 0? The alternative hypothesis is R is not equal to 0. Can I reject the null hypothesis? Why can I reject the null hypothesis when this is such a low correlation, so close to 0? Why can I reject? I can reject it because my significance, my p-value, is less than 0.05. So even though it's only a small correlation, then I can still say that it's statistically significant. I'm 95% sure it's a real correlation, that it's not equal to 0. It's equal to 0.2. It might be equal to 0.22, but it's not equal to 0. So it's a weak association, but it's a real association, statistically significant association. So now I can go ahead and do my regression, create that line, and actually I can click in here and show you the line. And I think I want this one. And there's that line. And that line has a formula. See, it created that line for me. So I actually see that line. Okay, there's my y-intercept, and there is my slope, 0.36. So 0.36 means for every y is the weight of the child, 0.36 is the weight gained by the mother. So for every 10 pounds that the mother increases her weight, that the weight of the child goes up by 3.6 ounces. Right? Okay, so that's one of the ways I might interpret this. Okay, so let's go ahead and do our regression. Analyze, correlate, regression rather, linear. I'm going to move the mother's weight gained and into the dependent variable, and then put the weight of the child in ounces. And I'm going to go ahead and calculate this. Let's see what I wind up with. Again, I get R is 0.222, and R squared is 0.05, is 5%. What does that mean to us? That means that 5% of the variability in the birth weight of the infant is due to the amount of weight that the mother gained. That's incredible. I don't know if that's true, right? I mean, this data came from real data. It's only a subset of real data, but I don't know if that's true. That means that really doesn't make much difference how much the weight the mother has gained in terms of what the final birth weight of the baby is. Probably the weeks of gestation probably have more. There may be other factors that have a much more important impact on the weight of the infant, such as weeks of gestation, whether the mother smokes, marital status, maybe some of the other variables here might have more of an impact than how much weight the mother gained. Okay, so let's see what we have in terms of our coefficients. And you saw this in the formula just a little while ago. the constant, the y-intercept is 105. I'm going to call it 106 for our purposes. And the weight gained is 0.361. This is the slope of our line. So if I open up a piece of paper here, what this tells me is that our formula for that line is going to be y is equal to b0 plus b1x, where b0 is the y-intercept. And what is that? That's equal to 106 plus the slope for the weight gain during pregnancy, which is 0.36 times the weight gained during pregnancy. So y is the birth weight of the baby, right? Is the birth weight in ounces. So my birth weight is equal to 106 plus 0.36 times the weight gained by the mother. Okay, so in other words, if I were to ask you, use your formula to predict how much the baby would weigh if the mother gained 20 pounds. Well, if the mother gained 20 pounds, we'd have 0.36 times 20 plus 106. So we would predict the birth weight would be, and this is going to be 7.2. So that 20 times 0.36 times 7.2. 106 plus 7.2 is going to be 113.2. We would predict that that baby would weigh 113.2 ounces based on our formula that we generated from our regression analysis. Okay, so we can use it predictively. Unfortunately, in this case, it's not that good a predictor. Well, let's see how bad a predictor it really is. Okay, so I can take advantage of the fact that actually, it's not just a matter of guessing. I know for this woman right here, the first one, I know how much weight she gained. She gained, where is it? She gained 38 pounds, and her baby weighed 111 ounces. This woman gained 32 pounds, her baby weighed 117. This woman gained 75 pounds, and her baby was 143 pounds. This one gained 52 pounds, and hers was only 112 pounds, less than almost the same as one that gained only 38 pounds, right? So we can see it's not too predictive. But let's see if I can't see, if I can't get an example that'll show me what the relationship here is. And if we had used our formula, in other words, if we plug in this woman's 38 pounds that she gained into the formula, how close to 111 is it going to be, the actual weight for her baby? So we can test how big the error is that our formula makes for each one of these women that we have real data for. That difference, that error, is called the residual. Okay, the residual. In other words, the difference between what our formula predicts and what the real weight of the baby was is called the residual. And we can actually ask SPSS to calculate that for that. So analyze. I'm going to go to regression, linear, and I'm going to go in here and I'm going to click on save. So just remember that it's a little bit weird because you might not intuitively think to go into save to do calculations. Looks like you're just going to save a file or something, right? So in here, we can ask it to calculate for us the predicted values. In other words, calculate based on this information, calculate what you think the birth of the infant would be, the weight of the infant would be, and then do the math and subtract the real weight, the weight that we calculated from the formula, and tell me what the residual is, what the difference is. So I'm going to click OK, and then click OK. And by magic, when I come back here, I have two new columns here, the predicted value and the residual value. So for the woman that gained 38 pounds, and her baby weighed 111 ounces, if we had applied the formula to her weight, in other words, here's her weight in the formula, we would have predicted that her baby would have weighed 119 ounces. It really only weighed 111. So we overestimated it by 8.4 pounds. That's our residual. And the same thing for this one with 32 pounds. It actually weighed 121, we underestimated it by 3.7 pounds because we would have guessed, we underestimated, we would have guessed it would have been 117. So you could, if I asked you, for instance, what would you expect the residual be for a woman number 21? Well, the residual is going to be, I can't see it there. Oh, we don't have the data. We don't have a weight gain for her. I picked a bad one, right? 17. Okay. For this woman who gained 31 pounds, her baby weighed only 88 ounces. We were way off on that one, right? We overestimated it by 28 ounces, right? So there was something else going on there. Was she a smoker? Not married, right? That was one of the risk factors. She was divorced, I think it looks like that. I can't, let's see. Mother did not smoke, so that's not a risk factor. Did she drink? She didn't drink. So whatever other reason, occasionally, things happen anyway, right? So at any rate, so that's how you would apply this. That's how you would create a formula that would help. Now, if we found, see, this isn't too encouraging. In other words, given what you know now, that for every 10 pounds a woman is going to extra 10 pounds a woman puts on, that you're only going to get 3.6 ounces, maybe more in the weight of a baby. If you're a doctor, you're saying to yourself, well, that's not a great trade-off. I'm going to encourage healthy eating, but I'm not going to take my patients and encourage them to pack on a lot of pounds because it's not very good predictor on increasing the birth weight of the baby, right? So you can use this to make a judgment, make a value judgment as to how you might proceed in a public health setting or in a clinical setting, and so on. So I think that should help you a bit. I did some stuff. I tried to stay away from anything specifically in terms of the types of data sets I gave you for the test, and but we did get a chance to review these two specific tests, chi-square, or three, correlation and regression. Get a chance to do that, and we also got a chance to review this idea of how to phrase a null hypothesis, an alternative hypothesis for all of the different kinds of hypothesis testing that we've done this semester. I think that was a valuable thing for us to do. Okay, so go and get the 100 on the test now. Okay? All you guys going to get 100 on the test now, right? Promise me? Okay, good. Excellent. And I'll be happy if you do the test, to be honest with you at this stage. We have very little time left. So I got to get grades in at some point. So if any of you decide to do a project instead, you are welcome to do that instead. And you can upload the project to Blackboard. It will allow you to do more than one upload. So if you upload it, I'll check it every day or so, every couple of times a day. And I'll check to see if anything's there. And if I see something there, I'll comment on it, maybe encourage you or something like that. But also, just to be extra nice, if you want, you can take a look at since you don't have to submit the exam, you don't have to submit the exam until you're done. You can take a peek at the exam and you can decide whether or not you want to continue on the exam or do a project instead. So you have a little extra latitude there as well. So good luck on the exam, and please work on it soon so you don't get you don't wind up in a time crunch at the end of the week. And remember to go back, and if you have any outstanding homework that you want to improve the grade on, but the grade or the project has to be in by Thursday midnight. The exam you have until Friday midnight to complete. Okay, the other stuff, grade and the homework and the project is going to take me more time to grade, so I need that sooner. But the exam I can hold out until Friday at midnight. Okay, so have a great rest of the summer, and I'll get this posted as soon as I can. And I know one of you had an issue with Blackboard. Hopefully that gets resolved. If it doesn't get resolved, let me know, and we can do it with that PDF file or something like that. Okay, take care, guys. Good night.